Hi class, in this lecture here we want to begin our discussion of the fundamental theorem of calculus. And so this lecture builds off the previous lecture when we were talking about how you find the area under some curve, okay, bounded above the x-axis and between two x values, x is equal to a and x is equal to b. And what we saw last class was, the way you would, find the area was you would build rectangles under that curve, and then you would take the limit as the number of rectangles went to infinity. And it was really, really complex. There was a lot going on. And then we ended that lecture talking about Riemann sums, and you could evaluate these Riemann sums using what we called a definite integral. And so what you saw was that we took the integral and we put what we called lower and upper limits or bounds of integration to it. And so in this lecture here, I'm going to show you how to evaluate or find a definite integral. All right, so all we're going to do here is we're going to evaluate the definite integral using this fundamental theorem of calculus. All right, and the fundamental theorem of calculus is really, really easy and really straightforward to use, and you'll see. Okay. So let's talk about anti-differentiation and the definite integral. So throughout this chapter, throughout these lectures that you've seen in the last couple lectures, you've been using this integral sign. Okay, so the integral sign here to denote an antiderivative. Okay, so like when you found anti-differentiation, this right here we saw was equal to f of x, capital F of x plus c. All right, and this was a family of functions because the constant of integration could be an infinite number of constants. And so now we have this definite integral. Okay, so this right here, when we solve this, right, remember that we're going to use this to find an area. This is going to be equal to some number. Okay, so it's no longer going to be a function. It's going to be equal to a number. All right, that's what we're driving towards with this, right? Because it's going to be used to find an area. All right, so this leads us to the fundamental theorem of calculus. So if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of that function f of x on the interval from a to b, then this is what happens. The definite integral from a to b of f of x dx is equal to capital F evaluated at b, which is the upper bound. So just so we're clear here, f here is the antiderivative of f of x. And once you find that, what you're going to do is you're going to plug in first here the upper limit of integration. And then you're going to subtract away the antiderivative evaluated for the lower limit of integration, those a and b's. Okay. So we've spent a lot of time, all right, in one of the previous lectures talking about how you find the antiderivative. So in all our examples today, we're going to relearn that process. There's going to be a lot of examples that we're going to work through. And this will be how you find the area. And so what I'm actually going to do in a coming slide here is I'm going to rework one of the examples we did in the previous lecture to show you that this fundamental theorem of calculus works. Okay, first though, just some guidelines for using this theorem. Okay, provided you can find the antiderivative of f, you now have a way to evaluate a definite integral without having to use the limit of a sum. Okay, so this is very good. Okay. All right, we don't want it to use that limit process. So let me just show you on the next slide here. This was that limit process that we learned previously. Okay, this is taken right from a previous slide here. And this was really, really terrible, really, really hard to do. So now we can evaluate this without using this limit process. Okay. When applying the fundamental theorem of calculus, this notation below is very convenient, and I will do it in every example here. So you have the definite integral from a to b of f of x dx. That's equal to, so the first thing I'll do is I'll find the antiderivative of f of x. All right, notice there's no plus c here. I'll talk about that in a second. And then I'll put this like half a parenthesis sign and then a to b here. All right, what this is saying is like, okay, plug b into this antiderivative and then subtract away, plug a into it. So for instance, if we evaluate this, the definite integral from 1 to 3 of x cubed dx, We know that the antiderivative of x cubed is x to the 4th over 4. So this is f of x. And then right here is the antiderivative, capital F of x. And this is saying, look, these over here are the bounds of integration. So plug 3 into it. So you get 3 to the 4th over 4. And then subtract away, plug 1 into it. All right, and you get 1 to the 4th over 4. And this ends up just being 20. All right. And as I've been saying here, it's not necessary to include a constant of integration c, because even when you do, look, you get plus c and then minus the c, so the c's are going to end up canceling here. So no longer do you need that constant of integration. It's not needed, okay? So when you're doing indefinite integrals, okay, without the bounds of integration, then you're going to need that plus c. When you're doing these definite integrals with bounds of integration, you do not need that plus c anymore. Okay, let me show you how that this works by reworking that this fundamental theorem of calculus here works by reworking this example here that we had. And even before I jump into it, I put into the slides here all the basic integration rules, right? Because they're really helpful to have as you go through this process. You'll notice that I'm going to come back to these quite a bit. Okay, so here was the problem. Let's find the area under the curve of f of x is equal to negative x squared plus 6 above the x-axis and between x is equal to 0, now using this fundamental theorem of calculus. Over here, this part here was the limit process from a previous lecture. And what we saw was that the area should be 28 over 3. All right, and so let's use this fundamental theorem to show that. Okay, so you're going to integrate from 0 to 2. Okay, so these are your a and b. The function negative x squared plus 6 dx. Okay, so when you integrate x squared, you get, so this is, the antiderivative is minus x cubed over 3 plus 6x. And I'm going to evaluate from 0 to 2. All right, so this was just solved just using this power rule right here. All right, so what the fundamental theorem of calculus says is, look, take these bounds and plug it in. So you have minus 2 cubed over 3 plus 6 times 2. Okay, that's just this first part here. I'm plugging in the top bound. And then I'm going to subtract away. I'm going to plug 0 in. So minus 0 cubed over 3 plus 6 times 0. And look, the 0 goes away, so that's fine. 2 cubed is 8. So this is minus 8/3, and then 6 times 2 is plus 12. Well, common denominator here is 3. Well, minus 8 plus 36, look. You get the same thing. You get the same result. Okay, and this process obviously is so much easier than the limit process. So now we can use this fundamental theorem of calculus here to very easily find the area under a curve. And this is it. And that's exactly how, like when we saw that the differentiation helped us do the limit process for the slope of the tangent line. Here, this integration and this definite integral is going to help us find area under the curve. So so much easier. Piece of cake here compared to that limit process here. All right, so all I want to do now in the coming slides is just work a bunch of examples so you can see, how all of this is done. Okay, so there's just going to be, I think I've got 8 examples coming up in the next couple slides. All right, so first off, all I want to do for these first few lectures here, or first few examples, is I'm going to give you the definite integral, okay, and I just want you to evaluate it. So let's try this one. Let's find the definite integral from 1 to 2, so this will be our first example, of 6x squared minus 3x dx. Okay, so I got my bounds of integration here, all right, from 1 to 2. So I got to find the antiderivative of this. So the 2 becomes a 3 divided by 3 with the 6 there. So I'll even work this out like this. This is 6 times x cubed over 3 minus 3 times x squared over 2. And I'm going to evaluate this from 1 to 2. So let me just clean this up, right? 6 divided by 3, this gets me 2x cubed minus 3/2 x squared. And I'm evaluating from 1 to 2. Okay, so the first thing I'm going to do, all right, what the fundamental theorem of calculus says is plug this 2 in. So this is 2 times 2 cubed minus 3 divided by 2 times 2 squared minus, and now I'm just going to plug 1 in, 2 times 1 cubed minus 3/2 times 1 squared. All right, so unfortunately now it's just, a little bit of arithmetic and you have to clean this up, right? So 2 cubed is 8 times 2 is 16 minus, let's see, 2 squared is 4 divided by 2 is 2, so minus 6. And then minus 2, and then minus plus 3/2. Well, look, 16 minus 6 is 10, minus 2, so this gets me just 8 plus 3/2. So this is 16 over 2 plus 3 over 2. This gets me 19 over 2. And that's the answer right there. So you can see here, it's just using our basic rules of differentiation, right? This right here was just the power rule from right here, okay? And then it was just using this fundamental theorem, just plug in the upper bound and then minus when you plug in the lower bound. All right, let's do another one here. Let's look at the definite integral from 0 to 8 of x to the 1/3 power dx. Okay, so here again, you're just going to define the antiderivative here, antidifferentiation here. You're just going to use the power rule. So this is x to the 1/3 plus 1 divided by 1/3 plus 1. And then you're going to evaluate from 0 to 8. So this is x to the 4/3 divided by 4/3. Evaluated from 0 to 8. So the 4/3 comes up as 3/4. X to the 4/3. Evaluated from 0 to 8. Well, now just apply the fundamental theorem, right? Plug in 8. So this is 3/4 times 8 to the 4/3 power minus, now plug in 0. 3/4 times 0 to the 4/3 power. All right, we'll do the third root first, right? So the third root of 8 is 2. Okay, 2 to the 4th power is 16. All right, I'll even write it like this. 4/3. And then I still have 2 to the 4th power. This is just 0 whenever you have a 0 in here. 2 to the 4th power is 16. And then, 4 makes the 16 of 4 times 3. This just gets you to 12. Right there. So once you get it here, it stops being calculus, right? Then here, you do apply the fundamental theorem to solve this here, but then it's just a lot of arithmetic you have to work through here. All right, let's move on. Let's try some, let's try some trig ones now, okay? Let's try this one. Let's integrate from 0 to pi. And let's look at sine of x minus 5 dx. All right, so what does sine integrate as? If you need to go back, sine integrates as negative cosine of x. So this is negative cosine of x minus, and then 5 integrates as 5x. I'm going to go from 0 to pi. All right, so fundamental theorem, plug in. So this is minus cosine of pi minus 5 times pi minus cosine of 0 minus 5 times 0. Okay. So now you just need to clean this up. And this is where you just got to be very meticulous. Cosine of pi is minus 1. So it's minus 1 minus 5 pi. Distribute the negative here. Negative becomes positive, and cosine of 0 is plus 1. And then this is just 0. Well, negative is a positive, so you have 1 plus 1. This gets me 2 minus 5 pi. So you just have to be careful with the trig stuff here, right? Like you just have to make sure you remember, cosine of pi is negative 1, cosine of 0 is 1 here, and then just clean it up. All right, let's try this one. Let's find the definite integral from pi over 4 to pi over 2 of 2 minus cosecant squared of x dx. All right. Whenever, a lot of times when you don't see sine and cosine, it's like, oh, okay, just have to be a little bit more meticulous, right? I'm going to have to, remember my rules of trigonometry here to help me evaluate this. All right, anyway, so integral of 2 is 2x. What is cosecant squared of x? Well, let's look back. That integrates as negative cotangent of x. So minus cotangent of x. And then I'm evaluating from pi over 4 to pi over 2. Well, look, negative becomes a positive. So this is 2x plus cotangent of x from pi over 4 to pi over 2. All right, let's just plug this in. Okay, so plugging in pi over 2, this is 2 times pi over 2 plus cotangent of pi over 2 minus 2 times pi over 4 plus cotangent of pi over 4. Okay, be careful here. Be very careful, right? If it helps to remember, just remember, cosine of x is equal to, cotangent of x is equal to cosine of x over sine of x, if that helps. Okay. 2 times pi over 2 is just pi. Cotangent of pi over 2, well, cosine of pi over 2 is 0, and this is 1, so this is 0. Minus, here, this becomes 2 pi over 4 or pi over 2. And then minus, what is, sorry, I wrote cosine, it should be cotangent. Cotangent of pi over 4. Well, right, so like cosine of pi over 4 and sine of pi over 4 are both square root of 2 over 2, so this is just 1. And then look, just cleaning this up, pi minus pi over 2 is just pi over 2, and then minus 1. We got it. All right. So again, you just have to be meticulous. If you notice, what I do in all these problems is like I write out every step, and I find that that helps. A lot of times, I for as long as I've been teaching, right? It's been a while. I've been teaching for a long time. Students who skip steps or try to do stuff in their head and don't write it down, it's very, very easy to make a mistake here. Okay, let's try this one. Let me actually ran out of a little space here, so let me put in a new slide here so we can just do some more examples here. Okay, sorry about that. Working on the fly here. All right, so let's do some more. So we did some. Let's do some other transcendental ones here. So here would be the fifth example here. Let's look at the integral from 0 to 1 of 3 to the x power plus 4 dx. Okay, here, 3 raised to the x powered, you're going to have to integrate using this rule right here. It looks like a to the x. So it's 1 over the natural log of a times a to the x. So this right here, this integrates as 1 over the natural log of 3 to the x, plus 4 integrates as 4x. And you're going to go from 0 to 1. Well, now just plug in 1. Okay? So this is 1 over the natural log of 3 times 3 to the first power, plus 4 times 1. Now plug in 0, minus 1 over the natural log of 3 to the 0 power, plus 4 times 0. Well, 3 to the first power is 1, or 3, excuse me. So this is 3 times 1 is 3 over the natural log of 3, plus 4. And 3 to the 0 power is 1. So minus 1 over the natural log of 3, and then this is 0. So just to clean this up, look, 3 minus 1, this is just 2 over the natural log of 3 plus 4. All right, let's look at this one. All right, this will be the last one we do, and then we'll move on to 2 different types of one. Let's look at the integral from -1 to 1 of e to the theta plus sine of theta d theta. Okay. Let's integrate. Integral of e to the theta is e to the theta. We know that the integral of sine is minus cosine. So this is minus cosine of theta. And then I'm going from -1 to 1. All right, so just plug in, right? Here I just use theta instead of x, doesn't matter. So this is e to the 1 minus cosine of 1 minus e to the minus 1 minus cosine of minus 1. So there's actually something you got to remember. So cosine is actually an even function. And so what that means is cosine of -1 is the same thing as cosine of 1. So let me plug that in. So this is e to the 1 minus cosine of 1 minus e to the minus 1 minus, now cosine of -1 is now the same thing as cosine of 1. So watch what happens. E to the first power is just e, minus cosine of 1, distribute here, minus e to the minus 1, minus becomes plus cosine of 1. Well, look what cancels out. Cosine of 1 minus cosine of 1 plus cosine of 1. This is just e minus e to the minus 1 here. So simplify however you can. Okay, and I know it's hard to remember your rules of trig, but you know, hopefully that makes sense. Okay, to be able to simplify that way. All right, let's now end by looking at two problems where it's not. I just don't give you the definite integrals. I ask you to find some area here. All right, so let's look at this one here. Okay, find the area given that's shown here. So this is the curve y is equal to x minus x squared. Okay, and I want to find this pink shaded area here. Well, look, I'm asking you to find the area between 0 and 1. So this area is equal to the integral from 0 to 1 of just this function here, x minus x squared dx. So look, when you integrate this, x is going to integrate as x squared over 2 minus x squared is going to integrate as x cubed over 3, and you're going to evaluate from 0 to 1. And hopefully you see, like when you plug in 0, everything just goes away. So you just have to plug in 1. So this ends up just being 1/2 minus 1/3, or 3/6 minus 2/6. This little pink shaded area here is just 1/6. And then finally, this area bounded by this region. Well, look, so y is equal to 5x squared plus 2. I'm telling you to go from x is equal to 2, from 0 to 2. So this is my A, this is my B. And y equals 0 tells me the x-axis. Okay, so I can just use this fundamental theorem. So I'm going to integrate from 0 to 2, 5x squared plus 2 dx. Well, look, this ends up being, when you integrate x squared, right? So this is 5x cubed over 3 plus 2x, and you're going from 0 to 2. Right, so now you can just, you know, you don't need to plug in 0 because it's going to wipe everything out here. Okay, so it's just 2. So this is 5 times 2 cubed over 2 plus 2 times 2. Well, notice there's a 2 down here, so this is really 5 times 2 squared when you cancel 1, plus 2 times 2. This is 5 times 4 plus 4. Well, 5 times 4 is 20. 20 plus 4 gets me 24. All right, so we've worked through a lot of examples here, and I hope that hope you have a good understanding, or starting to have a good understanding of the fundamental theorem of calculus here, and how to evaluate these definite integrals. And as always, if you have any questions, please let me know.